So now I want to get into aromaticity. Okay, so we've done nomenclature already. So now we need to figure out what is this thing called aromatic. Benzene was discovered by Michael Faraday in 1825, and he was the one who also found out that the ratio of carbon to hydrogen was 1:1, okay, in it, which is 1:1 means C6H6, right? So highly unsaturated compound. Now, the thing about why it's called aromatic is because it had a wonderful smell. Okay, so because it was wonderful smelling compound, it was called aromatic. It was classified as aromatic. Benzene is a name very specifically given to that one structure that he isolated. Now, the unsaturation here that we're talking about, 1:1, is really a lot of unsaturation, 4 degrees of unsaturation. You can calculate that. So 4 degrees of unsaturation is a lot of unsaturation for any compound. And the whole reason why we have this chapter now is because if benzene was behaving like a normal unsaturated compound, then it'd be fine. We'll be okay. Unsaturation means alkene or an alkyne. So if that was possible, then, we would not be having this discussion over here. So it didn't behave like that. Okay, benzene did not behave like that. And what do we mean by it didn't behave like that? Well, for that we need to look at the reactions. So what reactions do you want to look at? Okay, so if you have a high degree of unsaturation, then you would think, oh, okay, it can undergo addition reactions. Okay, so when you take an alkene, you treat that with bromine, that should undergo addition reaction. Treat it with potassium permanganate, it should give you a diol, give another addition reaction. But benzene is like, nope, nope, I'm not working. So benzene is not doing all those kind of reactions. Benzene, however, is undergoing substitution reaction with bromine, and that also in presence of a catalyst. So it's not undergoing addition reaction. Okay, remember there are 6 carbons and 6 hydrogens. Even to draw a structure for something with 4 degrees of unsaturation, you would need a lot of double bonds and triple bonds. So if you have that many double bonds and triple bonds, why are these reactions not working? And it means that the structure of benzene is not what everybody was thinking. So what can anybody think? Okay, so if you have a formula for C6H6, then you would first start drawing, a chain like this, 1, 2, 3, 4, 5, 6, and they're like, okay, I'm going to go ahead and put some triple bonds in there. So here is 1 hydrogen, 2, 3, 4, 5, 6. So I have now 6 hydrogens, right? So this should be fine, but that means that you're talking about a high degree of unsaturation and alkynes, which should give addition reaction. So that was not happening. Okay, so if that's not happening, the structure is definitely not what people were proposing at that time. So Kekule then came up with this structure of a cyclic nature. And the cyclic structure he proposed was something like this, okay, which meant that there was alternate double bonds and single bonds. And then this is how benzene is supposed to look like, okay, a cyclic structure of 6 carbons, okay, with alternate double bonds and single bonds. So this is all great. This was fine. Okay, so if you propose this structure, it means what? It means that you have a double bond here and a single bond here. So which means that when you do chlorination, which is substitution, okay, remember, we're not doing addition reaction anymore because addition reactions don't work on benzene. So this is substitution now. So when you do substitution on a benzene ring, then you should get 2 different kinds of products. In which case the chlorine is attached on a single bond like this, and one in which there is a double bond. Again, substitution, not addition, okay? But still, it would look like this. It would be different, but that's not what happened, okay? So they got only 1 compound in there, not 2 compounds, okay? So which means something else is going on in the ring structure. So then they said, okay, well, maybe then resonance is going on, okay, in the ring structure. And remember what resonance is. Resonance is movement of electrons in the bonds. So what's happening here? Here is the benzene ring, and then here is another benzene ring. Okay, and what is happening? Look at the double bonds. Okay, so they are kind of shifting around. So if I were to draw the arrows, it's really what's going on is this, right? And then you get the structure number 2 over here, and structure number 2 now has double bonds over here. Now this kind of resonance that is happening, it's happening so fast, so rapidly, that you can't tell the difference then between a single bond and a double bond. Okay, so if you can't do that, that means you can delocalize the electrons all over the benzene ring. Okay, and we have done that in resonance structures before. You know, when we write hybrid structures, sometimes we say, okay, you know, this is kind of what it looks like. So instead of writing dotted lines now, we are just going to go ahead and put a circle inside the benzene ring to show all that the double bonds are just rapidly moving around. Okay, and that is resonance structure. Now, how do you prove that? Number one proving was, of course, the dichlorinated structure, right? So there was only one structure that came out of that reaction that showed that, okay, you have only one type of bond. You don't have a single bond. You know, there's no double bond and a single bond. There is nothing like that. Okay, in a benzene ring, everything is equal. So the other way to prove that is by measuring the bond length. Okay, so the bond length that you measure, you should have that for a single bond and a double bond. Again, that did not happen. It turns out that the bond length is between a single bond and a double bond. So single bond is 1.54 angstrom and double bond is 1.34, but it turns out that benzene bond length is 1.4. So it's in between, right? In between, because it's very fast moving electrons, so sometimes single, sometimes double, and it's so fast that it gives the idea that the bond length is 1.4 angstrom. So something in between single bond, double bond. So resonance is one thing that is happening in the benzene ring. Okay, so that gives it a little bit of stability also, because remember, it's not doing any addition reactions as well. Okay, so if at double bonds, it should still react, right? So, but the double bonds are not doing any kind of addition reaction. So when there is this two problems going on, one was the problem of the structure, and the second problem we haven't solved yet is that of the reaction itself. Okay, why doesn't it undergo addition reactions? So the other point about stability in the benzene ring came about from the conjugation. Okay, so benzene ring is actually conjugated, right? Double bond, single bond, double bond, alternate. So which means that if you form any other kind of conjugated systems, then they should also be stable. Okay, they should also not do any reactions, because benzene is not doing any addition reactions, right? So other substances also should not do those kind of reactions. Wow. So cyclobutadiene, which is a cyclic ring with double bonds, okay, alternate double bond, single bond, it turns out it is so reactive that it dimerizes. Okay, so it gives a dimer like a Diels-Alder reaction, and so it's reacted, it's done. Okay, so nothing is happening there. Cyclooctatetraene was synthesized by Willstatter. Now this takes a long time to make. It's not like, you know, you can just go in the lab and churn it out. It takes time to make these kind of compounds. So once he made this, the whole idea was to see how it's going to react. Is it going to behave like benzene? And turns out it did not, which is also fine, because, you know, you prove something in there. It did not behave like benzene, which means what? It means it did addition reactions, okay, which is something that benzene is not doing. Benzene is not doing addition reactions, it's doing only substitution reactions. But cyclooctatetraene does the addition reactions just like an alkene would. Okay, so which means that there is something else going on, okay, in here. Okay, we have stability due to conjugation, we have stability due to resonance. This is all fine. The bond length we understand, all of that stuff we understand, but there is something else going on, and that something else was actually proposed by Huckel, and he proposed his theory of aromaticity to try to see why benzene is not reacting, okay, as an alkene should react. And his rules are now what we call aromaticity rules. So what are the rules? Here are the rules. There are 4 rules that we will study, and one rule is that the structure should be cyclic. Just keep benzene in mind as we are going through all of this. So in the 4 rules, the structure of benzene, or not benzene, any kind of an aromatic compound should be cyclic, which means that straight chains out. Okay, that's not going to be aromatic. Then each atom in the ring must have an unhybridized p orbital. Okay, so unhybridized p orbital meaning that you have a double bond, because remember double bonds have the pi electrons, okay, in there. So you have to have a p orbital, or you can also have a lone pair of electrons. Okay, so either you have a double bond or you have a lone pair of electron, but each atom must have it. Okay, now if you're thinking it's alternate, well, we'll talk about that. Okay, but each atom must have an unhybridized p orbital, so pi bond. Structure should be planar. Okay, planar means flat, all in one plane. Why? Because the non-bonding electrons have to overlap. That's the thing. If they cannot overlap, remember, you cannot have delocalization. And what we saw with all the reactions going on for benzene is that it's very stable. So if there was any kind of reactivity, then things would be different. Okay, but we know it's not. So which means that the ring has to be planar, because all those electrons that we see in benzene, they're all overlapping, giving it stability. Okay, and the overlap is that delocalization, okay, during resonance. Okay, and the last one point here, that's really the most important one here. Well, all of these points are important, okay, but this one, Huckel's rule, the number of electrons, this is kind of the key point. And what's the key point? That the structure should have Huckel's number, 4n plus 2 number of pi electrons, okay, should be in there. What does that mean, 4n plus 2? 4n plus 2 number of pi electrons should be present. So which means you calculate the number of pi electrons. So when n is equal to 0, then the pi electrons are 4 times 0 plus 2, which means 2 pi electrons. Okay. When n is equal to 1, that means 4 times 1 plus 2, and that is 6 pi. And so on and so forth. You can just increase by 4, right? That's what's going on here. So anything that has this number of pi electrons is going to be aromatic. Okay, now there are some exceptions. Of course, we will talk about those exceptions, okay, over here. But these numbers of electrons in any system should lead to aromaticity. Now, everything that we know about what we consider to be aromatic before is not anymore. So the only thing that we said before actually wasn't really that complicated. The only thing we said about aromatic was it's something that smells good, right? So now we're talking about aromaticity as a chemical property, as a physical property, okay, of a molecule. We're talking about very specific things that a molecule should have in order for it to be aromatic in nature. And again, what does aromatic mean for us now? Aromatic would mean that it does not react. It's very stable. It does substitution reactions like benzene, right? So it does substitution reactions. It does not do addition reactions. Those are the kind of things you have to think about. Okay, that's what means to be aromatic. Okay, so not moving on yet. Okay, just one or two more things over here. So first of all, if you just have the 2 pi electrons, that kind of structure cannot exist as aromatic structure, because remember, you need something to be a ring, and then you also need conjugation, okay, in there. So 2 pi structure does not exist like that for an aromatic structure. 6 pi structure, definitely there, that's benzene. Okay, so yeah, this whole thing is going to be about benzene for us. So 6 pi structure is benzene. The 10 pi structure is aromatic. It can be aromatic, but it is not aromatic because it's not planar. Okay, and I'll explain that to you. But it's not planar. All right, so that's why it's not. After that, so 14, 20, 24, all of the other systems, they're all okay. Okay, they're all going to be aromatic, no problem. It's just that the number 2 and 10, number of pi electrons, they are a little bit different. Okay, so even though 2 is a Huckel's number, there is no aromaticity, okay, for that compound, because even though the structure can be cyclic, but each atom may not have an unhybridized p orbital, okay, in there. So things, not quite systematic there, okay, we should say. But anyhow, the other thing I want to mention here is that you have pi electrons that fall in between also. So for example, we have 2 here and 6 here. These are the Huckel's number of electrons. But what about the 4 pi system? The 4 pi system, remember, was the cyclobutadiene that we just covered. Okay, so this is the 4 pi system. 1, 2, 3, 4, 4 pi electrons. So that 4 pi, which is missing from here, now that kind of a system is classified as anti-aromatic. Okay, so anything that is following all of the rules except for Huckel's number is anti-aromatic then. Okay, so then here 4 will be anti-aromatic, 8 will be anti-aromatic, 12, and so on and so. You get the idea. Okay, so that's how these work. So we're going to learn about some terms as we go on. So the terms that we have is 3. Okay, so something is going to be either aromatic, anti-aromatic, or non-aromatic. Okay, so 3 things they can be. So for aromatic, you have to follow all the 4 rules, okay, that Huckel's rule has, which is cyclic structure, unhybridized p orbitals. Generally, those are going to be conjugated systems, and then you should have a planar ring, follow the Huckel's number of electrons. Okay. For something to be anti-aromatic, as I just explained also in the previous one, everything 1, 2, 3 is fine, but not 4. Okay, so which means there is no Huckel's number for anti-aromatic. For the non-aromatic compound, you can have all of this, number 4 also in there, but maybe 1, 2, 3 is missing in there. Okay, so maybe the structure is not cyclic. Well, if it's not cyclic, you should not even think about it as aromatic. But maybe, it does not have all unhybridized p orbitals, or it's not planar structure. So in that case, it's going to be non-aromatic. All right, so 3 things that we are talking about: aromatic, anti-aromatic, and non-aromatic. Now, if you're wondering, what's the difference between anti-aromatic and non-aromatic? Really not a whole lot. Regarding the reactivity, anti-aromatics are quite reactive. Non-aromatic may be stable also, okay, which means they may not be as reactive. But anti-aromatic, generally like these two, they're not behaving like aromatic compounds, which means that they can do addition reactions, they can be reactive. Aromatic compounds are very stable, okay? That's the whole thing about aromaticity. This is why we've been talking about the resonance, the conjugation, all of that. That's coming because of stability. So aromaticity actually leads to stability, okay? So these 2 classifications, the anti and the non, they may not be stable. They can be also, but maybe not. Okay, so the anti-aromatic compounds that we have dealt with so far has been the cyclobutadiene and the cyclooctatetraene. I already went over these ones before, but now you can look at it from a different point of view. Okay, previously we were just looking at it as being cyclic and conjugated, alternate double bond, single bond. It should do reactions like benzene, and it didn't, because both of these were reactive when they were not supposed to be reactive, because they should behave like benzene, but they didn't. So in any case, so anti-aromatic compounds will just normally react as in like an alkene. Okay, now here are the 2 exceptions that I said I was going to talk to you about, and one of them is the 2 pi system, and then here is the 10 pi system. So the 2 pi system here is not aromatic because there is no conjugation. Why is there no conjugation? There is no conjugation because this is an sp3 carbon. This is sp2, this is sp2, okay? So which means you have a p orbital here, you have a p orbital here, but there is no p orbital there. So because of that, it's not going to be aromatic, all right? So there is no conjugation. The way I look at it easily enough is this conjugated or not, okay? So the 2 pi system, even though it has Huckel's number, it's not aromatic. The 10 pi system is a little bit different because for this one you actually need a model. Okay, so since you don't have a model, I kind of showed it to you over here, and I'll see if I can find a video to show you for this one to say that, if you make the model out of this 10 ring, okay, 10 carbon ring structure, The middle two carbons here with their hydrogens, remember each carbon has a hydrogen, okay? So, but the middle two carbons here with the hydrogens here, they start fighting with each other. There is not enough space. So because of that steric hindrance, the ring is a little bit twisted. And because of that twisting, the ring is out of plane, okay? And so because of it's out of plane, now all the p orbitals cannot overlap, because that's the main thing about uh, conjugation, okay, is that it should be able to overlap, and if it's not overlapping, it can't conjugate. So even though it has the alternate double bond single bond, there is no conjugation going on, okay? So these are the two exceptions. Just a little bit about molecular orbitals, okay, and the benzene rings. And I hope you don't find all of these molecular orbitals too crazy. But what I was trying to do over here is to try to draw orbitals to show you that when you have any kind of an orbital, remember that in any kind of molecular orbital, you have the wave functions, the plus and the minus. So all it is just different, the different colors, the brown and the blue one, they just show that they are not the same wave function. Okay, so when the orbitals are overlapping, they should be the same color. All right, and then you have a good overlap. If they are not the same color, at that point you end up getting a node. Okay, so I've shown you the roads here with the red line. Okay, so here these three are fine, these three are fine, but then here this is not fine, so here is the node, okay, in the middle. So the more nodes you have, the greater the instability, okay, or the less stable the compound is, and that's really what's going on here. So which means that the most stable structure regarding using the molecular orbital for benzene is when all of the wave functions are on the same side, okay, which is the lowest energy for benzene, and that's how it should be, because technically it's very stable. Okay, so the rings that I have shown you over here is showing you the overlap, which means that conjugation is going on. When you have a node, you cannot have conjugation going on. Okay, so nodes should not be there. So if everything is kind of the same color, the same wave function, it means that conjugation is going on. And that's why we can write the ring inside the benzene, right? So you can easily show this, and this kind of a ring is really what this is conjugation, okay, in benzene. So this is just the molecular orbital kind of structure with it, and the more imbalance you have of the orbitals, see here, blue, red, and then everything, there are so many nodes over here, so this is highly unstable. This is not going to form. This is the more stable structure for benzene. The other thing about the molecular orbital theory that one can do is what is called frost circles. Okay, and the frost circles, they look like this. So what frost circles tend to do is they write all the electrons that you would have in the pi system. So cyclobutadiene, for example, it has 4 electrons. So what you do is you take the cyclobutadiene, you can see that I have turned it around. It's not like a square. I mean, it is a square, but it is not drawn like this. Okay, I have not. I've kind of rotated that a little bit. So to give a pointy end here, pointy end here. Okay, so that pointy end is how you draw frost circles. And then since you have 4 pi electrons in there, you start filling out electrons. So remember how you fill electrons. You fill the lower energy first, you pair them, and then you do the other orbitals and you fill them singly first. And why singly over here? Because you have 2 orbitals here. So remember, if you are mixing 4 atomic orbitals, you will get 4 molecular orbitals, okay? And that's what we have over here with these orbitals. So there is 1, 2, 3, 4 molecular orbitals. Each of the carbon points over here is where the orbital exists, okay? You take your line and you draw it in the middle, and that's called the node. All right, so just in the middle, just slice it in the middle, and then that's called the node. So now when you fill electrons for cyclobutadiene, you have the 2 electrons over here, and then 1 electron each in nodes 2 and 3, which fall right on the node. Okay, and you're thinking, okay, so what's the big deal? Well, let's look at benzene. Benzene has 6 pi electrons, so 6 atomic orbitals, giving you 6 molecular orbitals. So 1, 2, 3, 4, 5, 6, right? That's what we have. So by the time you put the 6 electrons coming from the 6 atomic orbitals, all of them fall below the node line. Okay, so there is nothing on the node. So if you have any electrons on the node, then that compound becomes really quite reactive. Okay, so there is a lot more energy in it. So the same thing here I've done with cyclooctatetraene. So again, I've been drawing it like this before. And here are the double bonds. But now what I've done is I kind of rotated this also, so the pointy end is on the top and the pointy end is at the bottom, okay? And then again, you have now with cyclooctatetraene 8 atomic orbitals. So then you fill out those 8 electrons, and it turns out that 2 electrons will fall right on the node. And hence, cyclooctatetraene and cyclobutadiene very reactive because their 2 electrons are falling right on the node. Okay, that's what happens. So benzene very stable from the frost circle. Okay, so sometimes when you don't want to do anything and you can just go ahead and draw a frost circle and see if a compound is going to be reactive or not, but otherwise you can follow the Huckel's rules. All right, so one of the things that happens with aromaticity is that you have aromatic compounds like what we've been talking about so far, but everything that we've dealt with has been neutral. Okay, so now I want to talk about some compounds that can be converted into ions, and those ions then can be aromatic, anti-aromatic, or non-aromatic, whatever it is. Okay, so the first compound I want to take is this one, which is cyclopentadiene. Okay, and cyclopentadiene by itself is not aromatic at all. Okay, why is it not aromatic? And you can see that from the sp3 carbon that's over here. So remember, each carbon should have a pi bond. So the only way you can get a pi bond is if everything was sp2 or there was lone pair of electrons, which is not there. So this carbon is preventing conjugation of these electrons. So this is considered to be non-aromatic. Now, if you remove 2 electrons from this system, how do you remove electrons? Is by doing acid-base reactions. So you can either push electrons in a system or you can remove electrons from a system. So once you remove electrons in a system, now what happens? You create a carbocation. So that cation now can have conjugation. Why can it have conjugation? Is because now you can draw resonance structure, right? So if this is moving there, then the one resonance structure that you end up getting, oopsie, not there. And so then this is moving there, then you have this, and the double bond is still here. You draw the second one, and the second one will look like this, right? And that's there, and there is the carbocation. So because you can draw the resonance structures, it is more stable, okay, but it still doesn't have the Huckel's number. So because it doesn't have the Huckel's number, this is anti-aromatic, but it has all the other things. It is planar, it is conjugated, okay, all of those kind of things it still has. Now, once you push electrons into the system, now you have 2 more electrons. So 2, 4, 6. So now you have 6 pi electrons, and now this becomes an aromatic structure. Okay, so you can see how you can take something that is non-aromatic and then convert it into something that can be aromatic or it can be anti-aromatic. Now, why would you want to do that? Sometimes really it's just about research. Okay, you just want to see whether ions can behave in an aromatic way or not. And again, remember, how are we testing that? When something is aromatic, it will undergo substitution reactions, okay, and not addition reactions. So that's kind of what we mean by aromatic. The other thing is stability, and the reason why it doesn't add on do addition reactions is because it's very stable. Okay, so that's what happens when you push electrons or remove electrons from a 5-membered ring, okay, like this. This one here is about a 7-membered ring. Okay, so if you take a heptatriene, which looks like this, again, this is non-aromatic because you can see the sp3 carbon right here. Okay, so again, I can add 2 electrons or remove 2 electrons. So when I remove 2 electrons, now I've created a space over here, and that positive charge now, that means there is no electrons over there. So if there is no electrons there, that means I can go ahead and start doing conjugation. Okay, and I'm sorry, not conjugation, resonance structures. Okay, so here I can move all of these around, and if I can move them around, that means everything is conjugated. So conjugated, cyclic, 6 pi electrons, it's a planar structure. Yes, it's going to be aromatic then. Okay, so you can determine even with ions. Okay, so and then here's the anti-aromatic one, because now this one has 8 pi electrons when you push 2 electrons into the system. So now everything is conjugated, it is planar, cyclic, everything is there, but it doesn't follow Huckel's numbers. Okay, so that's why it's going to be anti-aromatic. So you should be able to do all of these, just follow the simple rules. Now, I generally don't kind of trick you into something, giving you something that is out of plane, okay? Because for that you need models. So sometimes you don't have that available. So generally I will not give you that as an issue, but all the other things you should be able to follow. Then there are also heterocyclic rings, okay, that can be aromatic. So in heterocyclic rings, what it is that you have one heteroatom, something other than carbon, in the ring. So here is nitrogen, this is pyrrole, here is oxygen, that's called furan. If you have sulfur, it's thiophene, and so on and so forth. Okay, so I have all these kind of heterocyclic rings. So what happens in these rings is that the lone pair of electrons from these atoms, they can also be involved in aromaticity. So in pyrrole, the nitrogen lone pair of electrons, that counts as the pi electrons that we are talking about, okay, the p orbital electrons. So 2, 4, 6, okay, 6 pi electrons. Now what happens in furan and thiophene, where you have 2 lone pair of electrons, only one of them is going to be involved in the aromaticity. The force of aromaticity is so much, okay? Why? Because it leads to stability, that it's not going to choose all the 4 electrons. So you're not going to count all the 4 electrons from oxygen into the system, okay? If the system needs only 2 electrons to be aromatic, it will just take those 2 electrons to become aromatic. So furan is aromatic, thiophene is aromatic, okay? Here you have something like 2 nitrogens, okay, in imidazole. So what happens here? These 2 electrons are involved in resonance. These 2 are not, okay, because they don't need to be, because right here is the double bond. Okay, so double bond, single bond, double bond, single bond. So now you have conjugation. These electrons do not need to participate in aromaticity. Now we're going to talk about what happens to these electrons too, okay? But right now, that's what we are talking about, is what kind of electrons are involved in aromaticity. In pyridine, the nitrogen electrons are not involved in aromaticity because they don't need to. Okay, it already has the 6 pi system, so they don't need to be involved. So you kind of get the idea of how you can use lone pair of electrons also for aromaticity. Okay, so as I said, I will talk to you a little bit about the nitrogens of the heterocyclic rings. And one of the things that nitrogen is for, a lot of our compounds is that it is a Lewis base. Why is it a Lewis base? Is because it has that lone pair of electrons. Okay, so if it can give that, then it is a Lewis base, which generally it can. So, but in heterocyclic rings, we have to figure that out. Okay, whether that nitrogen can give its electrons or not, because if it does give its electrons, it's a Lewis base, but if it doesn't, then it's not. But why will it not give its electrons? So the reason it will not give its electrons is because they are involved in aromaticity. So in case of pyrrole, the lone pair of electrons are in conjugation with the other electrons. So because of that, they're not available for reaction. So pyrrole has no basic nitrogen for that reason. Okay, so this lone pair of electrons, that does not make this nitrogen a Lewis base. Okay, on the other hand, pyridine, that lone pair of electron and nitrogen is completely available, okay, because all the three double bonds over there, those are the ones involved in aromaticity, which means that this lone pair of electrons on nitrogen does not need to be involved in aromaticity. So it is basic, okay. Now in this case where you have pyrimidine, you again have a benzene type ring with the two nitrogens. Both nitrogens are fine. Both of them have basic nitrogens, okay, on them, which means that they can behave like Lewis bases, no problem. In case of imidazole, you have one nitrogen that is involved in aromaticity, but the other one is not, okay? So the one that is not can then be basic in nature. So this one here can give its electron. This one, electrons are not available, okay, because they are involved in aromaticity. So that's what you do for all of these structures, okay? And is look if they are involved or not. So in this case, for example, in the last one, in the case of purine, if looking at all of these structures, see here is the double bond, double bond, double bond. Here is the double bond, lone pair of electron. So that's aromatic, which means this is available, available, available. Okay, so only one of the nitrogen electrons are not available. Now, if you're thinking, what's the big deal? It is a big deal, okay, because then your compound can be basic or neutral. Also, the lone pairs, they're involved in a lot of things, okay? So the nitrogens are also involved in hydrogen bonding, for example, and things like that. So you really have to understand nitrogen from, not just one point of view, okay, from different points of view. So we cannot just say that the electrons are going to be involved in aromaticity and we're done, we're not doing any more. But no, there is more to it, okay? And the more to it is that if the electrons are involved in aromaticity, then this is not basic, okay? And so you learn about the properties of substances that way, okay? And so you're not just focused on one thing, but learning about a little bit more. In the case of polynuclear aromatics, excuse me, in the case of polynuclear aromatics, if as soon as you have benzene rings, everything is going to be aromatic. You don't even have to think about it, okay? Because if you see benzene rings stacked on top of each other, side by side, on top, wherever, that's all aromatic, okay? So you don't have to think about it too much. So here is a solved problem for classifying something into aromatic, non-aromatic, etc., etc. So let's look at all of these that are given to us. So the first one here, which kind of looks like furan, but it is not furan. So is it aromatic? Non. It is non-aromatic because of that sp3 carbon in there. So the next one here, let's see, we've got electrons here, we've got electrons here, electrons here, but none over here. So remember, each carbon should have, sp2, it should be sp2, or it should have electrons. I mean, that's what happened here. So it's same thing, okay, with this structure over here, the dianion is not aromatic. Let's see what happened over here. So we have two electrons, that's it. So this is going to be anti-aromatic because there is conjugation, but not Huckel's number, okay, in here. In this case, let's see what's going on. So we have 2, 4, and then nitrogen is there. So we have lone pair of electrons there. And then we have a cation here. So because of that, we have a total of 6 electrons. And then all of them can be conjugated. And they're conjugated because of that positive, okay? If that positive was not there, it would be not aromatic, okay? But because of that positive, now this is an aromatic structure, okay? So let's look at this one, what's going on here. So 1, 2, 3, 4, 5. So that is 5 times 2, 10. Okay, so 10 is a Huckel's number, and there is conjugation, and every carbon has pi electrons. So yeah, that's going to be aromatic. Okay, so hopefully that helps you, okay, in your classifications. So I think that's it as far as we are concerned for aromaticity. Learn your Huckel's rules, and that should take care of everything.